Hello, my name is Jared Skeens and welcome to the Zoom room. Today I'd like to look at Statistics 1, Permutations and Combinations, Part 2, Problem Solving. So in Part 1, we looked at the strategies and kind of mental concepts that go into these permutation and combination type problems. And now that we've discussed that, now let's look at these Cambridge question types and put what we learned in part 1 into practice. So let's get right into these problems, and we'll look at the first one here. I'll screen share. So here we have Freddie has 6 toy cars and 3 toy buses, all different. He chooses 4 toys to take on holiday with him. In how many different ways can Freddie choose 4 toys? And then in the second part, how many of these choices will include both his favorite car and his favorite bus? So let's go back to our board here. So Freddie has 6 toy cars, 3 toy buses. So we notice that there's a total of 9. Total of 9 vehicles that he has. 6 cars, 3 buses, and he's going to choose 4 to take with him when he goes on his holiday. So our first question is, how many ways can he choose 4? So in our first one, this is a very straightforward question. We've got 9 vehicles to choose from. There's no restrictions on this. Remember last time we said, first, is this permutations or combinations? Well, we need to answer that question first, don't we? Since this is 4 going on the holiday, it doesn't matter whether it's the first one selected or the 4th one selected. It just matters that it's a part of the group that's going on the holiday. So this is a combinations question, not a permutations. We don't care what order the 4 toys are. We just want to know what 4 toys are in the group to go on holiday. So this first question, this is a combinations. Second one has to do with restrictions. There's no restrictions. So if there's no restrictions, we also don't need the number 3 question, which had to do with the strategies, which were more the categorical type restrictions. So we don't have that. And these are all different toys, so we don't have identicals. So this is a very basic, straightforward question. We have 9 toys total, and we want to choose 4. And if you do 9 choose 4 in your calculator, you'll get 126. So there's 126 different possible combinations of 4 toys that he could take with him on his holiday. Now we move to the second question. How many of these referring back to the 126, include his favorite car and his favorite bus? So we've got 4 toys chosen here. 1, 2, 3, 4. 4 toys were chosen. And we want to make sure for this question, out of these 4, his favorite car and his favorite bus are in this group. Okay, so in other words, we are already determining them to be a part of the group because that's what it's asking for. So that leaves us 2 slots left. Well, if 2 of the vehicles are already said to be chosen, then that means we now have 7 vehicles left to choose from. So for this part here, we then have 7 vehicles, choose 2. And when we do 7 choose 2 in our calculator, we get 21. So out of these 126 possible 4-toy combinations, 21 of those 126 will be combinations that do include his favorite car and his favorite bus. So that's our first example. And again, we'll use what we learned in the part 1 to help us think through our way through these questions as much as possible. Let me set up the second question. Okay, actually we're on the same question, but we're just moving on to parts III and IV. Says Freddie arranges these 9 toys in a line. So III, find the number of possible arrangements if the buses are all next to each other. Then in the next part, find the number of possible arrangements if there's a car at each end of the line and no buses are next to each other. So let's go back to our board here. So this is the same question. Still, Freddie has 6 cars and 3 buses, a total of 9. But now instead of choosing 4, he's arranging the 9 toys in a line. So we need, now that we've changed some information here, we need to go through our strategies again, our action plan. So the first question, is it permutation or combination? Is it an arrangement or a selection? In I and II, there was a selection for a holiday trip. So that was combinations. Now we're taking them out into a line and we're arranging them, meaning the order matters. So this is a permutation now. So we're in permutations and we now have this restriction. So here our keyword for permutation arrangements, and here we see these restrictions. So first restrictions, all the buses next to each other. In other words, they need to be together. So if we look at this, we're going to have 6 cars. So car 1, car 2, car 3, car 4, car 5, and car 6. Then the buses need to be next to each other. So things that need to be together are put into a group. So I put them in parentheses to show that they're one group. So this is bus 1, bus 2, and bus 3 are in this group together. So if we are numbering these, this counts as 1, 2, 3, 4, 5, 6, and this group is 7. So there are 7 items or groups in this line that needs arranging. So that is, 7 factorial ways of arranging the cars with the bus being arranged with them, the buses group. Now, within the group, there are 3 buses that also can be arranged. So this is times another 3 factorial. So we have 7 factorial times 3 factorial, which gives us a grand total of 30,240. So notice with the combinations, I used the NCR key on the calculator. When it comes to permutations, I prefer to use the factorial. It's still on the calculator, but it's not using the NPR key. So 7 factorial and 3 factorial. The 3 factorial had to do with, maybe I should put it like this. The 7 is the group, but then there's the 3 factorial ways of arranging within the group. So it comes out to 30,240. So we saw this idea also in the part 1 when we were looking at it. Now we want to do a similar thing where we're arranging it, but with different restrictions. So now we want a car at each end and no buses next to each other. In other words, the buses have to be separated or apart from each other. So in this case, we have to have a car at each end. So we'll start with car 1. And since the buses can't be together, it means there has to be a car between them. So we need to use spaces here. Spaces, car 1, car 2, space, car 3, space, car 4, space, car 5, space, and car 6. Now, normally with spaces, we also put spaces on the outside because as long as the buses aren't together, there could have been a bus over here as well. But it said that the cars need to be at the end, so that way we're not allowed to have extra spaces for the bus to go. The spaces need to be inside, not on the outside. So got to read carefully. The cars have to be at the end. So with this, there are 6 items, 6 factorial ways of arranging the cars. And then there are also 3 buses. So bus 1, bus 2, and bus 3. And so when bus 1 goes in, there's 1, 2, 3, 4, 5 spaces available for bus 1. So bus 1 could be in 5 different locations. So once bus 1 goes in, now there's only 4 spots left for bus 2 to choose from. And then once that one is filled in, then there's only 3 spaces left for the 3rd bus. So 5 different places bus 1 could go, then 4 different places for bus 2, 3 different places for bus 3. The other spaces don't matter. They can just collapse and erase them, get rid of them. It doesn't matter if cars are next to each other. We just can't have the buses next to each other. So 6 factorial times 5 times 4 times 3 gives us a grand total of 43,200 different arrangements of these 9 toys that satisfy these particular restrictions. So that's one complete Cambridge question. I don't know exactly how many points it was. I didn't pay attention to the points at the end, but one Cambridge question with 4 different, ways of asking the question, from the very simple, just straightforward, to from combinations to permutations, and also together, not together. So this one question hit a lot of the different things that we looked back in part 1 video for the permutations and combinations. So let's move on to a different question and see what we can do with that. Okay, here's our next question. Says a group of 6 teenagers go boating. There are 3 boats available. 1 boat has room for 3 people, 1 has room for 2 people, and 1 has room for 1 person. Find the number of different ways the group of 6 teenagers can be divided between the 3 boats. So we'll come back to our board here. So we have 6 teenagers, 3 boats. Boat 1 can hold 3, boat 2 can hold 2, boat 3 can hold 1. We see that the boats can hold all 6, but how many ways can these 6 teens be divided into these 3 different boats? So first thing, again, that first question, are we looking at permutations or combinations? In other words, does the order in which they're sitting in the boat matter, or does it just matter that there's 3 in this boat, 2 in this boat, 1 in this boat? This is a combinations because we're not concerned about where they're sitting, just that there's a group of 3 in this boat, a group of 2 in that boat, and the last person in the third boat. So this is combinations. Now, our restrictions, so to speak, are the capacity of the boats. So we're going to start with our first boat, and before anyone gets into a boat, there's all 6 teenagers standing there on the dock. So we're going to take 6 teenagers, and for this first boat, we want to choose 3 of those teenagers. Doesn't matter which 3, just any 3. 6, choose 3 for the first boat. Okay, so now we got 3 people in this first boat. Now, out of the 6, there's only 3 teens left standing on the dock. So for the next boat, we have 3 teens, and we need to choose 2 of those. Then, of course, for the last boat, there's 1 teen left. And so, of course, that teen is the one that's going to go into that last boat. So these get multiplied together. So since they're being multiplied together, it doesn't really matter which boat you start with. You could have started with the first boat. In fact, if you want to try just for fun, if you start with the first boat, it can only have 1 person. So you can have 6, choose 1. Then for the second boat, you would have 5 people left and you're choosing 2. And then for the last boat, you would have 3 people left, and of course, you're choosing all 3. So go ahead and check it out to see whether it matters which boat you start with. And so if we use our calculator and your NCR key, you have 6, choose 3, times 3, choose 2, times 1, choose 1, and you get 60 different ways. If we change the order in which we selected for the boats, if we did 6, choose 1, times 5, choose 2, times 3, choose 3, we still get 60. So it doesn't really matter which order you go in. You will still get 60 different ways that those 6 teenagers can be divided up into these 3 boats. So it's kind of a little different thinking process. Like I said, the action plan in part 1 doesn't cover everything, but it gives you a solid foundation to start with. And of course, these questions can be asked in numerous ways. So you're going to really have to think your way through, especially since your number of people are decreasing as you use them up. You know, as you put them into boats, your total is decreasing. So don't forget to adjust your numbers accordingly in situations like this. Okay, now let's move on to part B of the question. And I need to set it up first because it kind of completely hits a different area here. Okay, the second part of our question actually deals with numbers. They completely went in a different direction with the part B here. It says, find the number of different 7-digit numbers which can be formed from the 7 digits 2, 2, 3, 7, 7, 7, 8 in each of the following cases. So they give us these 7 digits. We have to find how many 7-digit numbers that can be formed from these 7 digits with the following restrictions. Letter I, the odd digits are together and the even digits are together. And then II, the 2s are not together. So let's come back to our board. And here again, we have our 7 digits, 2, 2, 3, 7, 7, 7, and 8. We want to make 7-digit numbers. For part I, we want the odds to be together, and we want the evens together. So let's start with the odds. The odds are 3, 7, 7, 7. They need to be together. and the evens, 2, 2, 8. So remember, our group is put into parentheses and counts as 1 as far as our line goes. And then these even are put into a group and count as 1s. So when we look at the groups, we have 2 groups. So that means we have 2 factorial, because we have 2 groups. So there's 2 times 1, or 2 factorial. There's 2 ways of arranging these 2 groups. Then inside our group here, there's 4. So that's a 4 factorial. And then inside this group here, there are 3. So that's a 3 factorial. So 2 factorial, the 2 groups, times 4 factorial, the ways of arranging the first group, times 3 factorial, the ways of arranging inside the second group. So this was what it's required to meet the restrictions. But if you remember, there was a 4th point in our action plan, and that had to do with identicals. So here we have identicals. We have 2s that are identical, and we have 7s that are identical. So that means we cannot distinguish which 7 is where and which 2 is where. So we need to get rid of these identical things so that we have distinct 7-digit numbers. In other words, we don't want to see the same number. It looks like the same. It's just the 7 switch place or 2 switch place, like that. So we have to take care of the identicals. Don't forget that. I mentioned that a lot of students forget that in the problem solving part. So there are 2 2s, so we need to divide by 2 factorial. And there are 3 7s, so we need to divide by 3 factorial. So you can either multiply all that out, or you can see that the 2 factorials cancel and the 3 factorials cancel, which basically just ends up giving you the 4 factorial. And so when you multiply 4 factorial, that gives you 24 different ways that you can, or 24 different 7-digit numbers that have the odds together and the evens together, and you can distinguish the numbers from each other. So that's one, part I. Now part II just says the 2s are not together, meaning they have to be apart. So if we ignore the 2s, that's 1, 2, 3, 4, 5 places here. So we have a slot, and then we have a space. You know, we have, let's say we'll just say our not 2s, okay? So not 2, our second not 2, our third not 2, our fourth not 2, fifth not 2. There's 1, 2, 3, 4, 5. Let me put a little more clear, and then space. So the 2s can't be together, which means they could be on the outside end or between the ends, as long as they're not next to each other. So the ends, it doesn't matter. So that's what we're going to start with. We'll put up here our 2s. Our first 2 and our second 2 have not been put in yet. So for the not 2s, there's no restrictions. So we start off with 5 factorial. Then there are 1, 2, 3, 4, 5, 6 different spaces that our first two could go into 6 different spaces, so times 6, and then that leaves 5 different spaces for the second two to go into. The other spaces just collapse. That doesn't affect anything. Also, don't forget, we still have the issue of identical numbers. So when we have our identical numbers, we still have 2 2s, and we still have 3 7s, right? So we calculate this, and when you calculate this on your calculator, you end up with 300 different ways that you can have 7 digits where the 2s are not together and they're still distinguishable numbers with respect to each other. So again, we saw this kind of strategy as well in our action plan in the previous video. So we went through 2 questions. Let's look at a different one. Okay, here's our next question. Says Mr. and Mrs. Keen and their 5 children all go to watch a football match together with their friends, Mr. and Mrs. Uzama, and their 2 children. Find the number of ways in which all 11 people can line up at the entrance in each of the following cases. So they're all 11 of these people are lining up in a line somewhere, maybe waiting to enter this football game. And this first case says Mr. Keen stands at the end of the line and Mr. Uzuma stands at the other end. So that's one thing we have to calculate. Then for the second case, the 5 Keen children all stand together and the Uzuma children both stand together. So let's come back to our board. So here we have Mr. Keen, I just call him Mr. K, Mrs. Keen, Mrs. K, the 5 Keen children, Mr. Uzuma, Mrs. Uzuma, and the 2 Uzuma children, total of 11 people. So the first thing that we want to ask ourselves again is this permutation or combinations. So in this case, because they're standing in a line and we're talking about ways of arrangement, this is permutation, not combination. Then we have a restriction. As they line up, the restriction is that Mr. Keen has to be at one end and Mr. Uzuma has to be at the other end. Now, they don't tell you which end they have to be at. So Mr. Keen and Mr. Uzuma make a 2 factorial because there are 2 ways that they could be at the end of the line. So Mr. K could be at the front, Mr. U could be at the back, or Mr. U could be at the front and Mr. K at the back. So we have that. Then out of the 11, that now leaves 9 people in the middle, and it doesn't have any restrictions about those 9. So this is just times 9 factorial, 9 factorial for the 9 for the first person, 8 for the second, all the way down to the last person. So 2 factorial times 9 factorial comes out to 725,000 and 760. 725,760 different ways of arranging these 2 families with the restriction that Mr. K and Mr. U are at either end. So that's the first part. Now the second part says that the only restrictions are that the 5 Keen children need to be together and the 2 Uzuma children need to be together. So let's go ahead and create our groups first. So we're going to have 1 through 5 for our Keen children group. And we're going to have 1 through 2 for our Uzama. 2 children need to be together. And then we have Mr. K, we have Mrs. K, we have Mr. U, and we have Mrs. U. So here we have 5, 6, 7, 8, 9, 10, 11. We got all 11, but because these are in a group, they only count as 1. So this is now 1, 2, 3, 4, 5, and 6. So this is going to be 6 factorial ways of arranging these 6 groups or persons. Then within the 5 children group, there are 5 factorial ways of arranging those. And within the Uzama children group, there are 2 factorial ways of arranging those 2. And we calculate that up and we get a total of 172,800 different arrangements with the restrictions that the 5 Keen children have to be together and the 2 Uzama children have to be together. So again, here's a little bit different twist, but again, there's also some similarities in our strategies and how we deal with grouping. So let's look at one more question. Okay, here's our last question. And let's pull it up for you so you can read it first. Says, find the number of ways that a committee of 6 people can be chosen from 8 men and 4 women if there must be at least twice as many men as there are women on the committee. So that's the first question. Second one says, find the number of ways a committee of 6 people can be chosen from 8 men and 4 women if 2 particular men refuse to be on the committee together. So we'll come back to our board. So again, we have a committee being chosen from this committee of 6. Committee of 6 to be chosen from 8 men and 4 women. If twice as many, there have to be twice as many men as there are women on the committee, or if 2 particular men refuse to be on the committee together. So again, our first question, is it combinations or permutations? Is this an issue of the way the people in the committee are sitting with respect to each other, or is it just a matter of they're on the committee or not? Well, this is about being selected to a committee. It does not matter the arrangement within the committee. So this is a combinations question. Then second of all, we look at the restrictions, which we've stated the restrictions. Then we want to choose a strategy. There is a general categorical strategy here, and that is we're going to have to make some cases for both of these. The reason we're going to have to make cases is because there are different ways that there can be twice as many men than women, and there also are different ways with respect to these 2 men who refuse to be together. So we want to set up cases for both of these. Let's go to our first one here. The cases that there are twice as many men as women. So let's start with there are 0 women. So twice times 0 is 0. So if you have 6 men, that's at least twice as many. I should have put at least here. I just put twice as many men as women. So maybe I should put here if twice as many, at least twice as many. Okay. So if we start with 0 women, then that means we have 6 positions available on the committee. And since this is combinations, we can just do 6 or 8 men, choose 6. So we're saying for this case, no women are chosen, which will satisfy our at least twice as many men than women. So if we're only using men, there's 8 men, and we're going to choose 6 of those 8. Second case is if there's 1 woman on the committee. So if there's 1 woman, that means there's a spot there, and then so 1 times 2 is 2 men. So that can work as well. There'll be at least twice as many men than women. So for the woman part, we need 1 woman and 5 men. So this here we need 6 men. Here we'll need 5 men. So for our 1 woman, there are 4 women. Choose 1 times 8 men, and we're only going to choose 5 for this one. Okay. Then for our next one, we can have 2 women. If we have 2 women, twice as many would be 4. 4 and 2 do make 6. So that will work as well. But obviously we cannot go on to 3 women because twice as many would be 6. 6 plus 3 is 9, and there's only 6 places on the committee. So now we want 2 women, 4 men. So we have 4 choose 2 times 8 choose 4. So when we do 8 choose 6, when we do 8 choose 6, we have 28. When we have 4 choose 1 times 8 choose 5, that gives us 224. This over. And when we have 4 choose 2 and 8 choose 4, that gives us 420. So when we add these all up, it gives us a grand total of 672 different committees that can be different 6-people committees that can be chosen from 8 men and 4 women, with the restriction that there has to be twice as many men as women. So notice we set up cases. Since there has to be twice as many men as women, we need to pay attention to how many were allowed into the committee. So with 0 women, we'll have at least twice as many. With 1, that means we have to have at least 2 men, no problem. With 2, have to have at least 4 men. That fills up the committee. We can't go more than 2 women. So here's our 3 different cases. Notice this one is just only men. 8 men, choose 6 of them. Here we have 1 woman being chosen out of 4, with 5 men being chosen out of 8. Here we have 2 women being chosen out of 4 and 4 men being chosen out of 8. You calculate each of these cases separately, and then you add them all together. So 672 different possible committees. Now we change the restriction, same committee, same number of men, same number of women. But now our restrictions are, there's 2 men, they don't get along, and they both don't want to be on the committee at the same time. So again, we're going to want to make cases here. So our first case is going to be if our man 1, first man, is not on the committee. So that means out of our 6, man 2 is going to be on the committee. So if man 2 is on the committee and man 1 is not on the committee, that leaves us with 5 spots left. There are a total of 8 and 4. There's a total of 12 people. So if we take off man 1, and we're declaring in this case he's not on the committee, and we have determined that man 2 is on the committee, so we remove those 2 people, meaning that there is still 10 people left for these 5 positions. So this will be 10 people. It doesn't matter the men and women. This is a different case, so don't be influenced by what you did up here. It's a different case, different restriction. So 10 people choose, and we have 5 slots left because we've already determined for this case that man 2 was going to be on the committee. Then we have not man 2, but man 1 will be on the committee. And you see that we have exactly the same scenario. So all we really need to do is multiply this by 2, because you still have this one not, this one is for sure. So there's still 5 spots left, and there's only 10 other people that we're talking about. So we have that. Then we also have the idea that neither M1 or M2 are on the committee. So that means there are 6 slots available. So again, we've said neither of these 2 will be on. So there are 10 people still available, but now there are, instead of 5 slots, there's 6 slots. So 10 choose 6. And so as we multiply this up, the 10 choose 5 is 252 times 2 gives us 504. And then our 10 choose 6 gives us, put this out here, 210. So we add those up, and that gives us 714 possible committee combinations where both M1 and M2, the 2 men that don't get along, won't be on the same committee at the same time. So it's okay for one of them to be on. It's okay for the other one to be on. It's also okay for neither of them to be on. They just can't be on the committee together. So you set up your cases involving those. When you determine someone to be on the committee, that just counts as like a multiply by 1, because you said that one person has to be there. But you need to make sure it reduces the slots, and these 2 people are now out of the question, so there are 10 people left. So make sure you're reducing your numbers correctly, and also realizing how many slots are left available. If you've already filled one of the slots, and both of these numerically work the same, doesn't matter which one's which, but they're 2 different people on the committee, so we have to multiply by 2, gives 504. This one with neither of them on, again, removing 2 people still gives you 10, but now all 6 slots are open because we didn't fill any of the slots. So 10 choose 6 gives 210. You add them up, you get 714. So I hope this is a sufficient sampling of the Cambridge questions to at least help you see why we had the video on the action plan to help you mentally prepare. And then as we implemented that action plan into our question types to solve the problems, hopefully the 2 together, the action plan plus working through some of the questions, will be helpful for you in achieving success on this particular Cambridge question type. So again, as always, thank you so much for joining me in the Zoom room, and I look forward to seeing you again next time.